Okay, we're doing number 11 from our homework. It says a 3-kilogram wooden box, so we're given that the mass of the box is equal to 3 kilograms. It slides from rest. Slides from rest. Oh no, these are the equations from chapter 2 again. So VI is equal to 0 because it starts from rest. And it slides down a 35-degree incline. How long does it take? So now I want to find the time to reach the bottom. Now they're telling me how long the incline is, 4.75 meters. And then they tell me the coefficient of friction, when it says wood on wood, that's mu, is equal to 0.30. So we have a lot of information here. Where am I even going to start on this problem? I'm going to start by drawing my free body diagram. Okay? So I'm going to draw my free body diagram showing all the forces acting on it. Okay? This angle here is 35 degrees. And here's my box. And I'm going to show all the forces acting. Now, remember, I want my sign convention to be in the direction in which it's moving. So look what I'm doing. I'm shifting my sign convention. I'm making down the incline positive instead of up the incline, because that's the way the box is moving. Okay, then I'm going to show all the forces acting on it. So if the box is moving, now is anyone pushing or pulling this box down the incline? No, it's moving because the angle's so big, like I just showed you before, that the component of the weight is pulling it. So there's no applied force. It's moving this way, so that means the frictional force goes in the opposite direction. The force of weight always acts straight down, and the normal force acts perpendicular to the surfaces in contact. So now I see I have all the forces acting on the object. Now, the first thing I'm going to say is free body diagrams have forces, and they gave me the mass. So one of the things is whenever I see that the mass, and I know I need the weight, I'll just go ahead and do that and say F of G is equal to mg. So it's equal to 3 kilograms times 9.8 meters per second squared. So F of G comes out to be 29.4 newtons. The only problem here is when I look at this problem, all my forces are not going perpendicular and parallel to the surfaces in contact. So here are the surfaces in contact, okay? This is the surfaces in contact. So I see F of F is parallel, F of N is perpendicular, but this one's not. So what I have to do is I have to take my weight and I have to break it up. Now this is where some people have a hard time visualizing. I want to take this force, F of G, and I need to break it up into horizontal and vertical components. So here's F of G. So what I'm going to do is I'll do it on this diagram. I'm going to draw an imaginary line from this point perpendicular to this surface like this. I just do a little dashed line in pencil. It's kind of hard for you to see. I'll do it in marker so you can see it. So here is the part that now is perpendicular. Now remember, components act in which direction? That components are perpendicular to one another. So now from the head of this one, I'm going to do another vector like this that's perpendicular to this, and this one has to be parallel. So this one is perpendicular, and this one is parallel. Now this is the part that goes back to geometry, okay? So you have to kind of visualize this in your mind. So this is just pretend this triangle here. I just made it smaller. So here's my 90-degree angle right there. Does everyone see that? If I take this triangle and I want it to go up here, here is this 35-degree angle. So now what I'm going to do is I'm going to flip it over like this, so the 90-degree angle's right there. Okay? And where's my 35-degree angle? It's the one that's up there. So the point of this is this angle here is similar to this angle here. Those are similar triangles. So now when I find the components here, here's FG. This one I'm gonna call this Y and this X because I like to use the same system that I use in math class. So this is going to be FGY. This is going to be FGX. This is my 90-degree angle that I just showed you because of geometry. These are similar triangles. Remember, this right angle here is similar to this right angle here. And because this is perpendicular to that and this is parallel to that, this angle and this angle are the same. So this angle here is 35 degrees. Now I just found f of g. It's 29.4. So now I can find FGX and FGY. So FGX, if I look at this triangle, is going to be FG times the sine of 35 degrees so FGX comes out to be 16.9 newtons. And then FGY is going to be FG cosine of 35 degrees. So FGY is equal to 24.1. Now remember, these two components, these replace this. So these two added head to tail equivalent to that. Once you draw your free body diagram showing all your forces going perpendicular and parallel to the surface in contact, then you're almost like home free. So what I'm going to do now is I'm going to redraw my picture. So here's my same picture. Here is my block. Remember, it's moving down the incline, so because it's moving down the incline, that's why I'm going to make my sign convention going in that direction, because when I apply Newton's second law, F is equal to ma, I want it to go in the direction of motion. So FF stays the same because the frictional force is always opposite the direction of motion. The normal force stays the same because the normal force is always perpendicular to the surfaces in contact. But now, instead of drawing FG, I'm going to replace it with FGY and FGX. Now, what's extremely important is, do you see here how when I took my F of G and I broke it up into components, you see how it's very important which way I have the arrows going. This is where I start. This is where I end up. So the head of this arrow goes this way, and the head of this arrow goes this way. So then when I put these components here, this direction is extremely important. All right, now, what did we learn before? Once we have all our forces going perpendicular and parallel, there's three things we do. Number one, we can sum forces in the y direction. We can sum forces in the x direction. And we use the mu equation. That's what we do on every problem. Now, this problem is more difficult than a lot of the other problems because they're not asking us for, like, the acceleration. They're not asking us for mu. They're asking us the time it takes. So before I start doing all this other stuff, when you don't know what to do, you go to the end. So what does that mean? You have no idea what to do next. So you go to the end and you say, what am I solving for? I'm solving for the time. Then you're going to look at the other information that I'm given in this problem. So I want to find the time. I have x. I know that VI is 0. Is there anything else I'm going to be able to find from this? What I'm going to be able to find from this, from these four things, is I'm going to be able to find the acceleration down the incline. Then I say to myself, I'm going to have four things. And once I have four things, I'm going to say which equation has these four variables, which x is equal to VIT plus 1/2 AT squared. So I'll have x is equal to 1/2 AT squared. And when I rearrange this equation algebraically, I multiply both sides by 2. I divide both sides by a. And then I take the square root. And then I'll be able to solve for t. So now I know I need to find the acceleration. And once I find the acceleration, somehow with this, I'll be able to substitute it in here. So where should I start? Well, usually we know the block isn't moving this way. So a lot of times it's easy just to start summing forces vertically. So we'll say summation of f of y is equal to ma. Is the block accelerating in this y direction? No, it's not even moving that way. So this is 0. I'm now going to replace this with all my forces going in the y direction. So I look at my free body diagram. Fn is positive. Minus Fgy is equal to 0. So Fn is equal to Fgy, which is equal to 24.1. I'm going to save summing forces in the x direction last because I know because I need the a, that's probably going to be the last thing I have to do. If I did it right now, I'd say, oh, I have too many unknowns. So I did this. So I got one thing done. Now I can use the mu equation. Mu is equal to f of f over f of n. So when I'm looking at that equation, and I'm going to say, well, what else do I need? Because they gave me mu in this problem, didn't they? Yeah, they told me that mu is 0.3. Yes. Okay, these steps don't necessarily have to be done in this order. But just to show you, let's say I did this next. See, the thing is, every problem is different. So you end up doing all three of these steps. So if I sum forces, so let's say I'd said summation of f of x is equal to ma. If I did this step, this is not 0 because I'm solving for a. In the x direction, fgx is positive. Minus f of f is equal to ma. So a is equal to fgx minus ff over m. Do I know a? No. Do I know f of f? No. So if I wrote this step next, which I can do, then I say, oh, there's two things I need to find out. I need to find f of f before I find a. So now I go back here, and I use my mu equation. So mu is f of f over f of n. So that's f of f is equal to mu times f of n. So f of f is equal to mu 0.3 times f of n, which is 24.1. So f of f did we figure out f of f? So f of okay, so 24.1 times 0.3 comes out to be 7.23. Now I can go back to this equation and say fgx, which fgx is 16.9, minus 7.23 over 3 kilograms, and that comes out to be 3.2 meters per second squared. And then why this problem is harder than any other problem on the homework is because now we go back to our equations from Chapter 2 right here. So now I'm going to go back here, and this is going to be 2 times x, which is 4.75, divided by the acceleration 3.2. So this one goes one step further than anything else, because once I found the acceleration, then I go back and find the time. Okay? And this is one of the things that these equations from Chapter 2 for straight line motion, those don't disappear. It's not like, oh, we took a test and we never have to look at those again. You see that these can come up, and one thing about physics and kinematics and all of mechanics are things are cumulative, and you have to remember these equations. That doesn't mean that every homework problem that we do, we're going to have to do all this, because we don't. This is the longest problem that there is. Okay? Most of the other problems, they're going to ask you, does this solve for mu? Well, they'll ask you to solve for the acceleration or something like that. So this one is the hardest problem. The only way to actually master these problems is practice, because every problem is going to be completely different. Practice makes perfect. That's why you do problems for homework. So as you do them, you become more comfortable. Okay?